It takes time, commitment, and a lot of hard work to build a body like Sonia or Eugene. But working out or walking down the street, any movement you make relies on a single, specialized body tissue.
With more muscle.
Muscles make things happen. They do work. This thermographic camera images body temperature. The more work you do, the more work your muscles do, the hotter you get. Muscle is the body's hardest working tissue. We normally think of individual muscles, but muscles are arranged in groups, each group moving a particular body part. Bodybuilders like Eugene and Sonia train using specific exercises for each muscle group. The muscles of the shoulders and back, or the legs, or chest. But they aren't building new muscles. Under the skin, you too could have a body like theirs. At least you have the same number of muscles. This is what we'd all look like if you peel off the skin and the thin layer of fat beneath it. Forget being made of skin and bone. Over half of your body weight is muscle. The most obvious are the muscles which move the body or maintain your posture, the ones you can see here. Each of these muscles is attached by tendons to the skeleton beneath, hence the name, skeletal muscle. There are over 400 different muscles in the body, each one responsible for the control of a particular range of movements. If the bones are the body's framework, the muscles are the pistons and motors which allow us to move. These are the muscles which we normally think of as muscle. They may be the most obvious, but they're certainly not the only ones. You might not think of your guts as being a mass of muscle, but they are. Food moves through these pipes because the walls contract, forcing it along. That means muscle at work. And then there's the most important single muscle in the body, a muscle that never gets tired, the heart. Wherever there is movement that you can see, there is muscle tissue at work. But how does muscle cause movement?
With more muscle.
Let's take a simple case. Sonia is lifting up a weight. Eugene is using the same joint, the elbow, but pushing down. But is it the same muscle that's doing the work? With these two, it's pretty easy to see that there's more than one muscle at work. Sonia's bulging bicep pulls the weight up. But when Eugene pushes down, you can see a different muscle at work, the back of his arm, the tricep. But why do we need two muscles for such a simple movement? Any individual muscle can only pull. The bicep contracts, pulling the arm up. But muscles can't push. They exert force only when they contract. So to move the arm in the opposite direction, you need another muscle on the opposite side of the joint. When the tricep contracts, it lowers the arm, while the bicep relaxes, and vice versa. Contraction is the key. To spot the muscle that's doing work, look for the one that's getting shorter during a movement. But how do muscles contract? Time to move from the gym to the laboratory. But first we need a likely subject. Bodybuilders aim to produce the biggest, the best defined muscles. But for our experimental subject, we're going to take an athlete who is aiming for something else. The ability to keep going for long periods of time. It's a different type of fitness. And athletes don't come much fitter than Alistair and Richard. They're triathletes, an event where they have to swim 1,500 meters, cycle 40 kilometers, and then run another 10K. Athletes who do one sport tend to develop particular muscles. Triathletes have to work on almost the whole body. And that makes Alistair almost ideal for a series of tests which will help us to investigate how muscle contracts.
Right, Alistair, if you just get on the chair here. What we're going to do next is...
First thing we're going to measure is how much force Alistair can generate with a single muscle, the one on the top of his thigh. Once strapped in, he'll push as hard as he can upwards against a force transducer. A single measurement of strength won't tell us much about how muscle contracts, but watch what happens as the leg restraint is moved into different positions before he pushes. Remember, as his leg moves up, the muscle we are measuring will become shorter.
Okay, are you ready? 3, 2, 1, go! That's good. Squeeze, squeeze, squeeze as hard as you can. You keep pushing, and relax. Just relax. Now your leg will be moved to a different position. So the length of the muscle is now changing. Right, so again, on my command, it'll be a hard squeeze for 5 seconds. Go! Hard as you can, hard as you can. Keep pushing, keep pushing, keep pushing. All the way as hard as you can, and relax there. Right, Alistair, we're in the final position now, so I want a maximal contraction from you on my command. Go! Squeeze, that's good, as hard as you can, keep squeezing, keep squeezing, keep
Changing the length of the muscle affects the amount of force it can produce. Interesting, but how does a muscle change length? To understand that, we have to have a microscopic look at muscle.
Great, that's the end of the test.
What we think of as a single muscle is made up of many muscle fibers. To understand the secret of muscles, we have to increase the magnification even further. No other tissue in the body has this distinctive striped appearance. Look closely at the pattern. Does it give you some idea of what happens when a muscle contracts? Think of a security grille. Inside the muscle fiber, it's much easier to understand with the help of a model. The distinctive pattern of muscle is made up from 2 sets of protein fibers. Here's the first set, a protein called actin, fixed at the ends and forming the vertical stripes you can see on the electron micrograph behind. But in between the actin fibers are filaments of another, thicker protein, myosin. The myosin filaments run in between the actin fibers like a mesh. If contraction is the key to understanding muscles, sliding is the key to understanding contraction. Watch what happens when the muscle mesh closes up. When the muscle relaxes, they slide back again. And just like the electron micrograph, the pattern repeats. Add in more groups of fibers and you can see how during a contraction, the sliding of the filaments shortens the whole muscle. That tells us what happens, but there's a missing element. Energy. Where does the energy come from?
With more muscle.
Muscles burn fuel, and to burn fuel, what do you need? Oxygen. First thing you notice whenever you ask your muscles to work hard is that you breathe harder. But what we're interested in isn't simply breathing, but respiration, how that oxygen is used. Let's take Alistair back into the lab and explore the relationship between oxygen and energy. With electrodes attached to the chest wall, we can monitor Alistair's heartbeat throughout the test. Changes in heart rate mean more or less blood being pumped to the working muscles.
Stay nice and relaxed, that's good. And just sit there and
But why the scuba diving gear? Well, we know the proportion of oxygen in the air he breathes. It's about 20%. So if we measure the volume of air he breathes in and the proportion of oxygen in the air he breathes out, we can calculate the amount of oxygen taken up by his body. First thing to do is to take a measurement when he's sitting there doing nothing, because even at rest, muscles and other body tissues need some oxygen to produce energy. This is his resting heart rate. Compare it with your own. Right. Time to get on the road. From the top, time from the start of the exercise, the heart rate, and the oxygen uptake. And now for the nasty part. How can we make sure that our subject is working as hard as possible? Well, make him work harder and harder until he can't go on. The treadmill will go at the same pace, but rising at the front throughout the test. He's going to be running up a steeper and steeper hill until he can't go any further.
Gone up again. Excellent effort. All the way through now. Put your hands on the side when you can't do any more. That's tremendous. Keep it going. Dig in. Keep your form. Keep your form. Okay, excellent. Well done.
On this experiment, when you can't go on, you really can't go on. But did you catch what was happening? Might be a good idea to take a second look.
So you can get off and have a little walk around.
Before the test, Alistair's heart rate was around 50 beats per minute, and he was taking up 4 mils of oxygen per kilogram of body weight. As soon as he started running, both figures increased sharply. They continued to increase as the treadmill got steeper. Until about 12 minutes in. There's a limit to the amount of oxygen any individual can take in. His heart rate leveled off, and you can't expect your muscles to work more if you can't supply them with more oxygen. He hit the wall. This is a test of aerobic exercise because it's dependent on the rate at which we can supply oxygen to our muscles. But why is the work our muscles do dependent on oxygen? Energy is produced in muscle by oxidation, the breakdown of glucose by reaction with oxygen. Glucose enters into a chain of chemical reactions, but it is only with the inclusion of oxygen that the end products, water and carbon dioxide, can be produced. So muscles need oxygen to burn their fuel, glucose. How does this produce energy? Energy released at various stages in this chemical reaction is stored by making a remarkable molecule called adenosine triphosphate, generally called ATP for short. Glucose and oxygen are continually reacting in the muscle cell, and ATP is continually produced. The energy stored in each ATP molecule can then be released to do work. Now it's finally back to those sliding muscle proteins. You've got it. It's the energy stored in ATP that enables them to move. Each strand of myosin protein has small projections sticking out like oars from a rowing boat. They touch the other protein, actin, and they really are like oars. The energy released by the breakdown of an ATP molecule causes the oars to move, pulling the myosin fiber along. Thousands of these tiny oars on every strand of myosin, each using energy from ATP, can row one protein along the other. That's the secret of the sliding filaments. It's a shame we can't see any of this going on in a muscle. But maybe we can with one of these, a magnetic resonance spectroscope. It's basically a huge magnet which allows researchers to study the activity of chemicals within the body without taking a sample. But before doing that, we can also adapt the magnet to produce an image of the muscle we're going to look at, one of the muscles in our subject's calf. Here's the lower leg in cross-section. The white line around the outside is the thin layer of fat beneath the skin. You can also see blood vessels, which show up in white, and the two leg bones, which are black. The grey areas are the different muscle groups in the lower leg. This is the one we're going to put to work. Our willing subject's foot is strapped into a treadmill, attached by a pulley to a weight on the far side of the magnet. After taking a resting measurement, she will continually move her foot up and down, working against the weight. The magnet is tuned to measure ATP-related compounds in the working muscle. Here's the spectrum of energy-related compounds in the resting muscle before she starts exercising. The three small bumps on the line represent the three phosphate groups in ATP. The area underneath shows the amount of ATP in the muscle. But how will that change as the subject exercises? Go. Here's the final result after 5 minutes of exercise. Other compounds change, but ATP remains the same. What does that tell you? That we produce ATP as fast as it's used.
With more muscle.
Aerobic exercise depends on oxygen. But what about this? A sprinter. Maximum effort, but in a short race he might not even take a breath. So where's the energy coming from? Glucose is broken down with oxygen in aerobic respiration. No oxygen and the later stages of this chemical chain can't be used. But some energy can still be produced anaerobically, without oxygen. The first few stages in the breakdown of glucose still produce some ATP. But if this works, why not use this anaerobic system all the time? Because instead of the reaction producing carbon dioxide and water, the end product is a chemical called lactic acid. Too much of that, and your muscles can't work anymore.
A tiny little scratch, you won't feel a thing.
Back in the lab with Alistair, and we can see what sort of exercise switches on this anaerobic system by measuring the level of lactic acid in his blood.
It's just a small...
After 10 minutes of easy running, his lactic acid level is only 1 millimole per milliliter of blood. He's exercising aerobically. But watch this.
1, go! Come on, Alistair, drive your legs, pump as fast as you can. That's good, that's a great start. Now keep it going.
Maximal effort for 30 seconds. Like a sprinter, you can see he's hardly breathing at all. So how will the level of lactic acid have changed?
That's good. Right through to the end, last couple of seconds, nearly there. And stop, and relax. Well done, good effort. There we go, 10.4 millimoles. So 10 times more lactic acid in your blood after only 30 seconds of anaerobic exercise, compared to that value of only 1 millimole after 10 minutes of aerobic exercise.
So there are two systems which produce energy for our muscles to do work. The aerobic system, when you can supply enough oxygen. This is the system for endurance. And the anaerobic system for short bursts of power. No need for oxygen, but you can't go on forever. Training is activity which increases the efficiency of the aerobic or anaerobic systems. But training depends on what you want. Sonia and Eugene are aiming to produce a particular effect, big muscles. What kind of training do you think they should do?
With more muscle.
We're all in training all the time, even when we're sitting down doing nothing, because our muscles are continually using energy, working against gravity. But what would happen to our muscles if they had nothing to work against?
Booster ignition and liftoff. Liftoff of Columbia on a multi-nation research flight.
In orbit, effectively there's no gravity, nothing for our muscles to work against. Astronauts on long flights find their muscles are much weaker. So how would you develop a system to keep your muscles working when weights don't weigh anything and you can't run because there's nothing to keep your feet on the ground?